Today, we're going to be talking about something that's pretty important. The topic is PyTorch and backpropagation. So this is, we think, one of the most important workshops out of the entirety of the workshops series because it shows you how PyTorch actually works behind the scenes, how the model is actually being trained. And we're going to be breaking down what we call the training loop line by line, so you understand exactly what's actually going on and why PyTorch and a lot of other machine learning libraries have made our lives so much easier trying to do machine learning and trying to train our models. So yeah, again, you can find the cluster over here. In there, you will find a link to the slides, and also today's guided project, it's part 3, so it's going to be the same guided project that you've been working on, but we're going to be going through the training loop, and at the very end, we may have a little friendly competition to like see who can get the highest accuracy. You don't have to participate, but like for people who have trained a particularly high accuracy model, we also do want to hear how you have designed your CNN architecture and how you have trained it, et cetera, et cetera. So without further ado, let's get started with exactly that. Oh, yeah, and some announcements, 2 announcements. So this Saturday, at Engineering 6, 289, 11 to 12 p.m., so right before the reading group, we have a little like course planning social, which is basically just some AI officers will show up early and like, enrollments coming around. If you have any questions of like, hey, what AI courses should I take? What should my course plan look like if I want to get into machine learning, if I want to learn more on a more, formal level? This is a place to be. Just kind of show up, ask some questions. We're going to have like one of our officers, actually, ex-president will be there, who is a math and computer science double major. We're gonna have the products officer over there, who is a math of comp and stats double major, and I'm obviously gonna be there, which is I'm a computer science major. So like a lot of our officers are a bunch of different majors. So if you're there and you want some tips on which classes are nice to take, that's a great place to go. It's just a little place for us to hang out. And right after that, we have our AI reading group, which is this week is going to be on federated learning attacks and defenses. How secure is your privacy preserving ML? It's going to be led by Benson, which you may know is actually the co-president for Cyber. It's a little collaboration, AI and Cyber, we've been doing for a while, and he's giving a talk on how, when companies say they are preserving your privacy using your data to train machine learning models, how are they actually doing that? They have to get access to your data somehow, right? This is what he's going to talk about. So yeah, that's going to be 12 to 2 p.m. at Engineering 6, 289. But without further ado, let's get started with PyTorch.
We're just going to give you guys a brief overview of the PyTorch framework, PyTorch library. And before we get started, if you guys have any questions on the functions and so on, and the multitude of classes we're going to be using, PyTorch has excellent documentation. So you can go to their website and get some extra information. Yeah, they also have good installation videos you can find on YouTube and so on. So yeah, we definitely recommend that. So let's start with tensors. So tensors are one of the essential building blocks of PyTorch. They're basically, it's a multi-dimensional matrix. And has anyone in here ever used NumPy? You guys know NumPy? So yeah, it's basically, a tensor is basically NumPy with gradients. That's basically what it is. It's those two things. You can actually convert a tensor to a NumPy array and vice versa. So you can go from a NumPy array to a tensor, and go from a tensor to a NumPy array. The only essential difference, I think, is the fact that gradients are stored for this tensor, so that you could go through backpropagation. So let's get into it. Yeah. After differentiation, in this case, we're talking about backward arithmetic differentiation. So torch initialization, and if you use this method right here, this is the simplest way to initialize a tensor. In this case, you're initializing the tensor with the first of 5.22.3, the second of 4.3, and 4. And if you print the tensor, this is what you get. And then if you print the shape of the tensor, you're going to get the dimensions of the tensor. I highly recommend that you guys use. And suppose the tensor is a tensor named y, for example, y.shape. If you guys ever have any troubles with your model, just print out the shape, because usually the culprits in the shape, your dimensions are, might be wrong. So yeah, that's how you create tensor. And right here, these are some really important methods that will come in handy as you work with PyTorch. One of them is torch.ones, which just fills a tensor with ones, the whole tensor. Another is torch.zeros, which fills it with zeros. Another is torch.rand. which fills a tensor with random values. And so in this case, you can see, like, you know, if you want to make a tensor Z, and you want to make with this dimension 5 by 2 by 3 dimensional tensor, and you want to make all the values of Z equal to 0, this is how you'd make it. And this is a multidimensional tensor. It's really hard to visualize in this way, but yeah, like that's how you'd make all the values equal to 0. Do you guys have any questions on this? No? Okay. And another very important function that you can get from the Torch library is the reshape function, which you give it a tensor and then it reshapes the tensor. So you're still having the same values, but you're reshaping the matrix into a different form, right? So in this case, you take a tensor of size, you take this tensor and then you reshape it to a new tensor that has dimensions 1 by 4 rather than just 2 by 2. So you're reshaping, you still have the same number of values, you just have a different tensor, but it's the same value essentially. This is a different object, but the same value. And then another relatively useful function is the squeeze function. So given a tensor, for example, that's 16 by 1, you're just reshaping it to 16 or 16 by 16 by 2 by 1. You're taking out the useless dimension and you're reshaping it back. Now it might seem kind of stupid, why would you need to reshape a tensor to essentially the same thing, but the way that PyTorch looks at a tensor that's 16 by 1 and 16 is actually different, and you'll run into issues when you're feeding it to a neural network. So another thing is, again, print the shape of your tensor. It's going to save you guys a lot of time. Yeah. Does anyone have any questions on this?
On the reshape, is there ever a reason not to squeeze it if you have these extra ones?
I guess if you're putting it into some custom layer or something, you might want to not squeeze it. Honestly, I don't see a reason. Do you guys know a reason?
Wait, is your question to why we are squeezing or why we are not squeezing?
If there's
is there a reason not to squeeze?
Right. So for example, let's say you are doing like a neural network and your input and your like weights matrix is like a 3 by 2 matrix, right? And basically what happens is if you want to multiply with some x, wx plus b, right? This x has to be a 2 by 1 matrix for you to get an output that is like y, which is 3 by 1, right? Because if you see dimensional multiplication, the inner dimensions of the match, there's the output dimension. However, in this case, it expects the x to be a 2 by 1 tensor, not just a tensor with dimension 2. So what happens is PyTorch will try to do this matrix multiplication and it goes, wait, I can't do that. And also, PyTorch has some other rules of like why sometimes you will want to squeeze. For example, it is called broadcasting, which is the idea of, let's say this x is actually not 2 by 1, it is b by 2 by 1, right? And b is the number of batch size. You want to do this wx operation to every single x in this batch. Then what PyTorch will do is we'll try to do like some dimension matching while ignoring some existing dimensions. And you telling PyTorch, oh, if you just put this in here, PyTorch will be like, well, 2 times b doesn't match, so your batch is like 64. This is going to give you an error. However, if you add a times 1, PyTorch will go, oh, this is your batch dimension. I'm just going to look at this instead. So like stuff like this is where like unsqueezing will help, and you will actually see like a lot of like more complicated neural network architecture implementations. They use unsqueezing very frequently, so they can take advantage of this broadcasting property. Because another thing is this broadcasting is done in parallel, right? So instead of using a for loop to like move through every x and doing this is done in parallel in the GPU. So that's why this is very, very fast. Does that make sense? Yeah. Yes.
So the parameter for the reshape function, is that the row and column for the new matrix?
Just parameter for the. Yes. So like
the one for.
Yeah, this is basically the shape of the new matrix, basically. And like again, like it's not just row and column anymore. You can have a bunch of different dimensions. You can make it like 1, 1, 1, 1, 1, 1, 1, 4, and it will still be okay. Just have a bunch of like extra dimensions you've added that are one dimensional. Oh, that have a length of 1.
Thank you very much.
Does that make sense? Okay, cool.
And some potential operations that you can use in using the Torch library for tensor. One is just adding tensor, and the result is just the element-wise addition. of the tensor, the way you do it is just very like simple, and that does make it very helpful. Another thing is called the Hadamard product, which just takes two tensors, multiplies each tensor element-wise, and then the resulting tensor has element-wise multiplication values, and that you just take a tensor, multiply it, and then so everything is very clear in that the way it was created like this is so that it's easy to use. And while doing this, later you'll learn that all the gradients for this vector, for these operations are also not computed here, but the tree is computed. So later you can use backprops to figure out the derivative of something with respect to x, y, or so on. So yeah. Anyone have any questions on this?
But basically, this operation is a little bit different from like the matrix, like especially multiplication, right? So it's different from matrix like operation, and it does not change the size for the torch.
Yep, it doesn't change that. It is different from multiplication. We'll show you guys how you can like multiply and so on, but it is different, yeah.
Oh, is a Hadamard product different from a dot product?
Yes, it is, because the dot product sends a vector and another vector to a real number, to a scalar, while the Hadamard product, you still have the tensor of the same size. It's just that every single value is multiplied together. So if you guys had like you guys had so the first one is dot product, and the second one is a
Hadamard product or tensor product. Basically, what we do is you're almost like expanding this, like you're basically doing this. 1 times 2, 3, and then 2 times 2. You're looking at every possible pair of them being multiplied together. So that'll get you 1 times 2, 3 just 2, 3, and then 2 times 2, 3 is 4, 6, right? Does that kind of make sense? Yeah. So again, like you're not gonna be working with this when you're building the neural network model. Dot products will all be working with, but not Hadamard products. The reason why I want to show you Hadamard products is because when you do backpropagation, PyTorch does a lot of this behind the scenes, because like Bayes' derivatives can get really annoying and complicated very, very quickly. But yeah. Oh wait, no. This is a tensor product. The Hadamard product is just a pairwise multiplication.
yeah, that's how it's like kind of confused.
Yeah, never mind. Yeah, sorry. This is tensor product. This is a separate thing.
Yeah.
Yeah. But yeah, a good way to remember this is a dot product, the output is a single number. The Hadamard product, the output is basically like the same as the inputs. And the tensor product is something that's much bigger. It's usually like each dimension of them like multiplied together. So that's kind of 3 that you can look at here. Okay. My bad. Yes, tensor product.
So if you guys might be wondering why all these operations are like, if you would ever use it, you actually do use it in a lot of like neural networks. One way you could use it potentially is to mask a tensor. So you can zero out part of the tensor, you can have part of the tensor there. So like in transformers and so on, this might actually be very, very helpful. And so hit this.
Like for example, if you have input system XYZ, you can do a Hadamard product of, let's say I only want the central entry. You can do a Hadamard with 0, 1, 0. And what this does is it creates a mask, because x times 0 is 0, right? Y times 1 is y. Z times 0 is just 0 again. So this basically allows you to only have the middle value and everything be what the value originally is, and everything else be 0. So you can do like masking and stuff like that. So you can actually take away information, which sometimes is what you want to train neural network. Say if you wanted to predict what these two are, for example.
Like very helpful. And another thing is the torch.matmul. I believe this is the same function in NumPy as well. And this takes two tensor and it produces the matrix multiplication of those two tensors. And so this is exactly the mathematical relation as well. Yeah. So you take two tensors, in this case x and y, and then you put them through matmul, and then it results in another function z. And a good way to check if everything is working as it should, again, print the shape of the tensor and see if your shapes are aligning properly. So yeah.
Yeah. And one important thing to remember is when you're saying multiplying A and B together in PyTorch, if you use the multiplication sign, like little asterisk thing, that's not doing matrix multiplication. That's doing the Hadamard product. We're doing a pairwise multiplication. So sometimes that's what you want, but sometimes that's not what you want. If you want to do a proper matrix multiplication, use the @ symbol or use matmul if you want to type up a full function. So that is a little like nuance here. It's like sometimes you're like, oh, I have two matrices and multiply them together. It's the @ symbol. Unless you're doing Heidelberg products, the pairwise multiplication, you're going to be using the @ symbol if you're doing like linear algebra matrix multiplication. Does that make sense?
And that's the same thing in NumPy too. So
Yeah, same thing in NumPy. It's all the same syntax.
it's basically the same thing, guys.
Yeah.
You know? So yeah, so we're gonna give you guys a brief overview of some important classes using PyTorch. This is gonna be pretty helpful today on the guided project. So 3 really important PyTorch classes. The first is the dataset class. Then we have the data loader class, and we have the module class. And we'll go into depth of each one. Let's start with the dataset class. So the dataset class is basically the class that controls your dataset. It controls your data, and you'd usually make a dataset for your validation and your training and your testing dataset. So yeah, this right here is the initialization state, the initialization function for the class, and this class is defined for PyTorch, and so you just have to import it. And yep, we'll explain what each of the functions are, and we'll explain what each of the functions do. I think in the self-explanatory, this is just the length of the data set, and this is getting an item from your data set so that it becomes easier to use the data set class. And this is now we're going in depth into each function of the data set. So first, just the constructor. It defines the attributes of the data that your data set will have. Probably the most important thing are your statements, which will be the inputs of the model, and your truth, which will be the outputs of the model. Yeah, so you can always have more attributes if you want in your model. And one good example, for example, would be an input to your data set class would be the images, for example, of the MNIST data set, or the images of the CIFAR data set, and the outputs would be the labels. So yeah, that is the data set class. Does anyone have any questions on this?
Again, this looks very complicated. PyTorch a lot of times will give us like pre-built data sets, like for cyclops and whatnot. But this is like if you say you got like a folder of images and a folder of like text files where it's like, oh, that contains the labels to the images. And you're like, if I want to create a custom data set to work with a lot of PyTorch things, this is how you would do it. So like if you like look into PyTorch source code, for example, the data set that loads Cypher 10 is really just a really big class that handles the downloading, and then if you get an item, fetch this image and its corresponding label. Like if you look into the source code, this is what's all behind the scenes, and that's why it's very convenient for us to just load a bunch of data and you just work. Yeah.
And just to give you guys like sort of an overview of what this is achieving. So anytime you guys build a machine learning model, you always have the question first, like, what am I building this up? You don't want to waste your time. And once you do know what you're building, you want the data, right? And so you get the data, right? And then you put it into the data set class. And then now you want to wait to load your data. So you use the data loader class to load your data. We'll explain what that is. And then you train. Yeah, then you train. So this is the essential workflow that you're going to use in PyTorch. So anytime you guys see a data set class and a data loader class and so on, this is what they're achieving, right? This is the flow that and the mindset that you want to get into while creating a machine learning model. And yeah, we already explained what the get item is. You just get an item from your data set. And then this is just a tuple of the input and the output, which is just a label in this case. Yeah, this just returns the length of your data set. And
and just a quick thing. Okay, can go back to get item. This is a little like Python thing. So like if you go back one more to get item, you're wondering, it's like, what is this double underscore doing in front, right? So in Python, one thing you can do for an object, sometimes you will be able to initialize an object and basically treat it as a list. And you'll be like, how in the world can we just treat something like a list with the square brackets to index it, right? This is how it is. Self-index. Basically, what this defines is it says we have this object, If we were to try to access it like a list, or even iterate through it like a list, and we were at, say, trying to access index 3, for example, this is what the behavior of a function is, and it is defined by getItem. So that is why we can take a data set and literally just say, I want the third item in the data set, and we'll get you a third item in the data set. Because under the hood, what Python's doing is just calling getItem while passing your indexing and do whatever you want while returning it. Does that kind of make sense? Yeah. And same with the next slide. Same with the len keyword. All that does is it allows you to be able to create an instance of your object and call len on it. And when you call len on it, all it is doing is calling the len function. So basically we're writing these like primitive functions of Python so that we can just try to understand things for our data set, and we will be able to understand it. So that's basically what's happening.
Yep.
Yeah.
And to give you guys the example on the guided project of the data set,
Zoom in a little bit. Yeah.
Zoom in a little bit.
Plus.
Is that good?
Yeah.
A little bit more.
Yeah, also can just
Zoom in.
yeah, like that.
Thank you, Jordan. You're a lifesaver, man. Yeah, so this is the training data set and test data set. Usually you make separate classes for each data set. And so in this case, you're using this for the Safari 10. This is available online in a server PyTorch uses. And yeah, so this is just telling you that this is not going to be used for training, that this is the testing data set, because they're separate files, and this is just converting it, it's just transforming it to a tensor. It's just transforming it to the tensor, and the download is just telling you that you're downloading it from a server. So yep, this is a data set class, and this is how you would initialize it for the Safari 10.
And technically, the transform and download keywords aren't keywords that you need when you're defining data sets. It's just with most PyTorch built-in data sets, they have the transform keyword defined, they have the download keyword defined, which is just they have an if statement somewhere saying if download equals true, check if it's downloaded. If it's not, go W gets the actual file or something. Again, it's just implementation details. It is not how every single PyTorch data set is going to look, but with most of them that's built in, it's going to look like that. Yes.
So the name of this function CIFAR10,
yeah,
is that the same as the root of the files?
Sidebar10 is just a particular class that is predefined for you. So Sidebar10 in this case, it is it inherits the dataset class, right? If you remember, you guys may have gone there, you may have gone there, but with objects you can inherit a class. It inherits the dataset class, and specifically it deals with the Sidebar10 dataset. Dataset name is just called Sidebar10, but if you actually look into it, it downloads to a very specific .torch repository, like directory on your computer.
So is that like you import the torch from the library and then you directly get those data from the library, or you're from the local files?
It is, you can get it from local files, but usually it directly gets it from the library. And you can see here roots. What this is this is by default where it's being downloaded to. So you can, for example, define, oh, I want it to be downloaded to the folder I'm currently working in. So next time if I were to try to call this dataset object again, it won't just download another copy of it. It will actually look in this folder and be like, is it there? It's there. Cool. I'm not going to do the downloading for.
Yeah, you can actually see where it's downloading it from. It's downloading it from CS Toronto. So because it's so far, it stands for the Canadian Advanced Institute for Research, something like that, Institute for Advanced Research. So that's where it's downloading it from their server. Yeah. So when you're doing this, so if you don't have internet, I don't think this is gonna work. So it's just built into PyTorch, because this is a very, very famous data set right here.
Yes. You will have to well, it downloads it for you, but you will have to do it because that's where our data set is, and you want to train your model. That's how you have to do it. Does that make sense?
Yeah.
Yeah.
Yeah. That's the data set class. Any more questions on that? Just another example of a custom data set.
We can skip this.
Skip this.
Yeah.
Explain that. And yes, explain that as well. So this right here is another class. It's called the data loader class. It's essentially it's a primitive in PyTorch. What it does is it takes a data set class and it wraps it around an iterable. So you can basically just call that iterable, and it gives you a batch with the corresponding labels, right? So now that you have the data set, you need to load it somehow so that you can train it. And you need an effective way to actually do this. And the data loader is your effective way. It shuffles it for you. It it puts it in batches and it gives it to you. So it does all of the sort of management of your data set in the background, and it just gives it to you in a few lines. So this just makes it more efficient. The thing is, you can actually do this by yourself. It's totally possible. It's just going to take a long time. So PyTorch gives you an easier way to do it. So this is an example of a data loader. It takes your training data set and test data set. Again, you make two different data loaders for your training and testing data set, and you give it the batch size, which in this case is 16, and then shuffle, which just randomizes it, right? And then you make that true. So it randomizes your training data. And then just to give you guys an example of your train loader, we have it right here. In this case, for the guided project, we have batches of 128. So as we increase the number of batches, eventually it will be the total number in your training data set. And at that point, you're just doing, gradient descent. In this case, you're doing batch gradient descent. And as you decrease it, as you approach 1, then you'll start to go closer and closer and closer to stochastic gradient descent. So yeah, and as you can see, it is an iterable. So you can. Did we print it? Yeah. So you can get one. One iteration of your train loader, and then you get the first image from your train loader. In this case, it would literally give you 120 images, and then you get the first image and the first label, and then you print the image and the label, and then that gives you your image and label. So in this case, I have no idea what this is. What is this? Yeah, but as you can see, it gives you your image.
So kind of to recap, the data set essentially says, given we have downloaded a bunch of these files, how do we load these files to become PyTorch tensors? The data loader says, given we have a data set that allows us to get these PyTorch tensors, how do we put them in batches so we can feed them into a machine learning model for training and inference? So that's kind of the two goals. That's why you define data set first, and you will need to pass the data set into the initialization of the data loader, because the data loader needs the data set to be able to load and match data set.
It's essentially a wrapper around your data set. That's all it does. It's so yep, that's an example of a data loader class and data loader iteration. Like that, you just invoke the train iterator next, and you receive a new batch of data from your train from your data set. And the good thing is, as you invoke this over the number of batches you have in your data set, you're never going to get the same one. It's always a new one, a new one, a new one until you finish your data set. And so in this case, when you're looking at the evidence data set, which is also another pretty famous data set. You guys know what the evidence is? This is show of hands. You guys know? Yep. So it's essentially just digit classification data set. I would encourage you to look at that as well. It's pretty cool. You have digits from 0 until 9, and it's a 26 by 26 image. It's it's just one channel, it's just grayscale basically, and it's made in a way that every single image is either a digits from 0 until 9. You're supposed to classify them to the corresponding digit. And this is a very good data set. Specifically, it's sort of like the hello world of machine learning, of neural networks, right? So if you guys are interested in doing this, I highly encourage it. It's an excellent project to start with, and yeah. Now, does anyone have any questions on this? Okay, so now we're going to get into building a model. So at the base of our model, the super class, essentially the parent class, is called the module NN module class. So that's the class that controls all the important aspects of a layer in PyTorch, right? So it controls the parameters, it controls the different workings, the inner workings of your layer, and you build it on top of it. So you have your NN module class, and then on the base, on the file, on subclass, you have your custom class that you're going to make. And so the two important functions you're going to have is initially you're going to have your constructor, which this super word right here inherits the attributes and the function of the super class. And this forward function, this is just forward propagation. So this is your model actually working from an input. So you have an input X, and this forward function outputs a corresponding output. So that's basically the gist of it. This is how you build your model. And yeah.
If you're wondering why use nn.module, why not just define a PyTorch class with all the similar like operations defined? It's because nn.module has a lot of really nice things built in to the PyTorch class itself. Like for example, we can use one command to just move our entire model from the CPU to the GPU, which you would want to do when you're training, or it automatically makes sure that all the model parameters that you're using, it will track the gradients of those tensors, and for any nested modules within this module, it will also track the gradients of those tensors as well. Like for example, the CNN layer is just a PyTorch module. The fully connected torch.linear layer it's just also just a module. Every single thing in PyTorch that's remotely like abstracted for you nicely is going to be a PyTorch module. And basically you just have a bunch of nested modules that, because of how the module class works, whenever you say, oh, I want to see what all the model weights are, what they all look like, it will just like do all the things to fetch all the weights inside each module and just like show you what the weights look like. So it's really nice in that way, and that's why you want to use in modules, because it makes, you don't have to think about like the idea of like, oh wait, technically this thing is wrapping the other thing. It just does it for you. Does that make sense? Yeah.
Does anyone have any questions on that? Okay. So yeah, this is an example of a module class. This is an example of your custom model that you make, custom model 1. So you make a first layer, which is a linear layer. You have your input dimensions and your outputs on 256 dimensional output. And note that the batches are actually sort of hidden in this case. You actually don't see the batches, right? You only see sort of a single, almost like a single training instance. But PyTorch handles it for this case. For some other cases, it doesn't. Suppose you make your own special operations, you will have to actually consider the batches as well. So keep that in mind. It's just hidden. It's just hidden rather than actually seeing it. This is because this is a custom. This is the pre-made class by PyTorch. So this one takes an input, the output set. Then this one takes that output dimension, then outputs 128 dimensional vector, and then so on. So let's see. You have your first layer, right? Which takes in your input dim, your input, and then outputs it into the second layer, right? And then so on. And you output it into another layer, and that's what you're representing. Right? This is what a linear layer is. It's just one layer of the feed forward your network and so on. Yep, and then finally you get the output dimensions with that. You get a vector of output dim, the dimension that you want. So this is a simple feed forward neural network. And then also in the forward function, you define this actual operation. So you go through what it, now that you have these components, how do you bring these components together? So you take your inputs, you put it through the first layer, you put it through an activation function, then you take that, then you do the same thing until finally you just output it. And yeah, does anyone have any questions on this? So you have all your objects, you just bring them together now.
And you can see in the notebook as well. We have defined the CN model, like the actual notebook itself.
Yeah. Oh. And let's show them that. So right here we have our CNN module, sorry, CNN model, and we're calling the structure of our superclass, and then these are the different layers that we have.
If we scroll down, you'll see that we have initialized all these particular layers, and we're saying, okay, in our for function, this is how we get from our inputs all the way to our output. We just keep on applying these layers, and we have some X at the end.
It's kind of cool because, one thing I really like about using this format is that it's easily usable. So like if you want to test out a different layer, you can just easily call an extra linear layer. You can, call a dropout layer, rationalization, and so on. It's easily usable. It's sort of like playing Legos. You can, bring one piece into another piece and so on and build on top of that. Also, another thing I want to note is that there's something called a sequential, which, NN sequential, which you can sort of group all of these layers into one sort of super layer. And then you can call that sequential object rather than having the tedious thing of this whole thing. Suppose you have a really gigantic number of layers. You can put it into one object called the sequential. You can just call that sequential rather than continuously calling this over and over again. That's also one thing to note while using this. So yeah, now we're going to go into training. So yeah, during training, one important thing is to initialize your loss and your optimizer. In this case, we're going to use the cross entropy loss, and we're going to use the atom optimizer. As we talked about last time, picking a correct optimizer is very important. It can lead to faster conversions times and a faster conversion time and a better local minima. And yeah. Let's give you guys an overview of the code that we have. And this is where we define our loss right there. We have our cost entropy loss, and right there we have our optimizer, which is our atom optimizer. And when you're defining an optimizer, you want to give it the model parameters, right? So because during the model updates, the optimizer is going to control how these parameters are updated. And then you also want to give it different parameters. For example, this LR right here is the learning rate. So the learning rate is going to be 0.003, and the weight decay is for L2 regularization, the weight decay factor. You guys remember last time when we talked about L2 regularization, there was a factor called lambda, right? This is what this is doing. This acts as a regularization technique. If your model gets too complex, it sort of decreases the complexity of the model by having a penalty on the weights.
When we say decreases the complexity of the model, we're basically saying that is a parameter that makes sure the actual value or like the magnitude of each entry of the model weights doesn't get too big. Because something machine learning scientists have found out is that when you have really, really big weights, because you're doing soft maxing, what happens is that your loss landscape is really jagged and like a lot of really steep slopes. Whereas when we keep it smaller, it actually becomes much smoother, which is why we actually want weight decay to both prevents a bit of overfitting. And also, because if you think about just really steep slopes, we have really steep minimums as well. That's a sign of overfitting, because the moment you change your input a little bit, you're somewhere else in the loss landscape, and it suddenly becomes very, very, very different. So that's why we have weight decay.
Yeah, the equation is essentially the square sum of all the weights together. That's what's added to your loss. And let's go to the next slide. And then to go into what the training loop is doing. So usually in your code, you're not going to define this as an extra class or something. You're just going to define it as a loop where you loop through each epoch of your training, and then you loop through each batch of your training. And so one thing that I want you guys to note is that the number of epochs you're going to use for your training is also really important, right? Because if you go too far into, let's say you have a data set and you have 100 epochs, right? Versus 10 epochs, 100 epochs isn't necessarily better. It might actually be worse because it might lead to overfitting. Because if you show your model the same data over and over and over and over and over again, it's going to memorize the data rather than generalizing for the data. And so what essentially happens is this leads to, poor, amazing training accuracy and very poor validation accuracy. I remember one time I had like a 99% accuracy on the Safari, and I thought I was a genius. I was like, this is amazing. But then it turned out that I just had to hide like a large epoch number. So please keep that in mind. And then to come back to the function. So the top loop is just iterating over the epoch, and the bottom loop is just iterating over your data, iterating over the batch. And then what this is doing is this is the tuple, your data. So like I said before, the training data loader is an iterable. So you can using iter keyword, you can get a data tuple, right? And the data tuple has your batch inputs and the batch labels, which are this is the batch that I have, and these are the corresponding labels, the corresponding truths, right? What is each of my training insights? For example, if you have images, this is a 0, this is a 1 digit, or this is a catalog, this is a dot. Those are what your labels are, right? So it has the tuples, and then we'll explain what this is doing. But just to give you guys a brief overview, this is just zeroing out the gradients of your parameters. And we'll explain why that is. We will explain it. It's something to do with backpropagation. And yeah. So This is for backpropagation, and this right here is getting the predictions of your model. Also, if you guys are wondering what the torch reshape thing is doing, suppose, for example, in this case, we're using the MNIST data set. This is an old site. We're not using the MNIST for our guided project. We're using the Safar, but the MNIST data set has a 26 by 26 image, right? And the batch size in this model was 16. So you have a 16 by 784 image 16 by 784 tensor that you want at the end. But initially, the tensor is actually 26 by 26 by the number of batches you have, which is in this case 16, right? But when you input this batch into a neural network, you want to flatten out the vector. So that's why you reshape the vector so that you give it a flattened out version of your vector rather than the previous vector. And so yeah, these are just the predictions right here. You predict you give your model the inputs, and you get the prediction, and then you find what the loss is, right? You calculate the loss. So you can sort of think about the loss as a final layer, because that's what you're going to use for backpropagation. You calculate the loss, and then you go backward, and then we will explain all the rest of that. Yeah.
Testing is just
Testing is
training,
just
but instead of like attribute backpropagation, you're saying, oh, what's the output? Does it match the input? If it matches, what's what's the accuracy? Like what's the probability, or like the number of times when it does match and when it doesn't match, and you say how accurate the model is that way. Yeah. And
if it ever gets too confusing, you guys can do this by simple for loops, because sometimes the functions can get too confusing. I've been in that position too. You can just make it like the argmax and stuff. You can just loop through the tensor and say, okay, which one is my highest value, and make this the prediction. It's that easy. It's just that these functions make it much easier. And this is just a visualization of your model. Visualizations help us understand. It's not as important, but yeah, visualization. And finally, another very key thing is to save your model. So once you have your model, you want to use it, right? So you save it into a file, and you save it so the dictionary of all the parameters of your models are saved to the relative layer, to the relative tensors. And so you save it in this way. And when you load it this way. One key thing to note is that when you load it, you need to load it into a model of the same format. So you guys just can't load it. You need to load it to the model of the same format. Because if the models aren't the same format, loading is going to have an issue, right? If you have a CNN and you're trying to load a feed-forward neural network into the CNN, you're going to have trouble. So, keep that in mind as well. And yeah, let's take a quick break. Does anyone have any questions on this? Anyone have any questions on this? Oh, all right, perfect. Yeah.
Okay. Yeah. All right, guys. So hope that quick break was nice. Now we're going to get into backpropagation. As you mentioned, I would. So backpropagation is how we actually update the gradients of our neural network models. So as we see here in this training code, we have inputs, data, yada yada yada, and then we do the zero grad, my model, predictions, current loss, and then current loss dot backward is where we actually compute this gradient and where we implement backpropagation, and then optimizer dot step steps in the direction of the gradient. Well, the opposite direction, but of what we just computed. So now how do we actually compute this? So we use matrix calculus, and that is a lot of it. As you know, the weights are a matrix, and we basically just do a whole bunch of calculus, and as we'll see in a minute, lots of derivatives, chain rule, math. It's just math. That is the secret ingredient to backpropagation right there. So to give some intuition, we could say one of our input layers is here as it takes in X and then it transforms to Y. We can think of that process as some type of function. In our case, it's going to oftentimes be an activation function. However, as we see here, F can be any type, can actually be any function. So yeah. So this might be, so this layer right here might be X, this might be Y, this could be Z. It's basically yeah.
For the notation, the bold letters are matrices, not vector?
I think the capital letters are. The capital letters.
So usually we use capital letters to indicate matrices and lowercase to indicate vectors. But again, like this is an example of like the very simple like logistic regression, where, like, you know, Ws plus B, right? But then the thing is, this can be anything, right? This can be anything we define and know how we mathematically have defined it. So it's literally just any function.
Yeah, it's not like there's a specific rule as to what it has to be. It's just we say, oh, it's that way because it's just how it is. Yeah, I mean, that's basically yeah. Okay, yeah. So if we have our input layers, we get this. If we have a lot of layers, we have this massive composition. Fn of Fn minus 1 of Fn minus 2 all the way to F1 of x equals y. And then once we add the loss or the cost function as well, we get yet another composition for y. So that finally gives us our loss. And then with that, we get the gradient, which is we compute the partial derivative with respect to the weight. But how do we calculate this? Well, we got to reformulate some notation here. So even though F1 through Fn of x and C of y are all functions that take in some x and y, it also depends on the weights. So really, it's actually F1 of x and W1, F2x and W2, and so on and so forth, and then C of y. So we could actually omit the x and y because we really don't care about the weights. So if you wanted to, you could just think of it F1 of W1 and F2 of W2, and so on and so forth. So an attempt might be we could try to nudge the weight by some small amount, epsilon, and see how much it changes, which is basically exactly the definition of a derivative. Now, unfortunately, this isn't exactly what we want because, as we'll get into later, it's too simplistic, and as we see, it's just the notation is questionable at best. So the good is we can always use the method. Even if we don't know what f is, it's all good. Problem is it's extremely inefficient. When computing, like when doing neural network stuff is already computationally expensive, this is the absolute last thing we need. If we use this, you're gonna have to evaluate f of 100,000 one times. Like,
Yeah.
what's that?
Okay, so basically the idea is that this attempt of like what's happening here, you guys may have seen this as like the definition of what a derivative is when you don't have access to what f is, what you can do to try to calculate a gradient is basically say, okay, we have our weights and we have our we can get the output, right? Let's take the first dimension of the weight and nudge it by some really small epsilon. And let's see how the output changes. And we use this to figure out the derivative of the first weight with respect to the loss function. We do it with the second weight. We do the same with the third weight. We do the same with the fourth. So kind of nudging each one just a little bit and seeing how that changes. That's the definition of a derivative, or a nice approximation of derivative. But the issue is, for every single weight that you will have to call x that many times. You have to do this nudging every single time. So hence, if we have 100,000 weights, we have to call f 100,001 times because we also have to evaluate x on the thing itself. So that's very, very computationally expensive, and sometimes it may be imprecise, especially if you don't choose. If you choose a really small epsilon, then you may run into numerical errors where like because we're working with floating point numbers, you may run into numerical errors. And if you choose a large epsilon, it may be a really bad approximation of what the gradient actually is. So yeah.
Basically, it's just no good. So what we actually use is our friend chain rule. So as a recap of chain rule, if we have a composition g of f of x, we get dg over df with respect to df times df with respect to dx, and we can use the same idea for neural networks. And what we're going to wind up getting is, a lot of gradients, lots of chain rule. Just so we do it for each layer. So dc over fn with respect to, so we can write dc with respect to fn and fn with respect to w. But what this really turns into is c with respect to fn, fn with respect to fn minus 1, fn minus 1 with respect to weights, and on and on and on and on. all the way until we get down to F1. And that's our gradient.
That's the gradient right there. Easy.
Yep. Yeah. Too complicated, skill issue. Yeah, it's a lot to look at. So yeah, here's our gradient, and then partial, and then obviously you might have noticed delta instead of d. What does the partial derivative mean exactly? And don't they only work for constant functions? Not exactly, because if we have f2y and f3 from y to z, we can go, and so we can do a two-dimensional x to a four-dimensional y. So like if it's 2 by 1 and y 1 by 4, it'll go from 2 to 4. Yeah, basically like
It goes from 2 dimensions, 4 dimensions, to 3 dimensions.
Yep.
If we have that, you go to the next slide. Basically, delta F3 of delta F2 is this crap.
this.
Right? So
Yeah.
you may be like, what is this? So this is something called the Jacobian. Who here has heard of the Jacobian? Who here has heard of it because they were in Math 32A? Yeah. So basically you will encounter this at some point in Math 32A. And what the Jacobian basically is you have all the inputs of your function, which is a multidimensional vector, all the outputs of your function, which is a multidimensional vector. It just says, look at every single possible pair of your input and output, because they're just, a vector with a bunch of entries. What is the derivative of one of the entries with respect to the other one of the entries? And you have that as a whole matrix.
Yeah.
Yeah. So again, like when we start multiplying these together, you can kind of see how, the derivatives, you start to have this almost like linear combination derivatives. It starts to work out to be the same as derivatives of more common neural network layers. But this is the basis. So like when we see delta of like y to delta x, delta of a vector output to delta of a vector output, this is what we mean. It's just a bunch of matrices. Yeah.
Yeah, it gets, so as you see here, we have so if we have F3, we have so 1 with respect to 2, and then 3 with respect to 2. It gets, it's definitely hard to look at. I think the right one's a little bit clearer, but as we can see here, it's still a lot of variables to see. It's basically how like each variable is changing with respect to every other variable, pretty much. So when we plot out each combination, we get the Jacobian. So these are just matrix multiplications. Now, but how does this actually work in practice? How does PyTorch know what the partial derivatives are? Well, it's going to know what function we're using. So if we use neural network conv two dimension, linear, ReLU, for example, ReLU, we know it's 0, 1. So it's going to know that the derivative is 1 for x greater than 0 and 0 otherwise. At 0, it's not defined, but that's kind of glossing over that. Because these operators are predetermined, PyTorch knows what they are, and so it can just have them.
Basically, if you have a definition for, hey, here's how you're doing the convolutional operation, we have the mathematical definition of that we implement to code. We can then mathematically derive, here's what the derivative of that convolution operation would be, and then mathematically implement that into code. So basically, we have these predetermined operation and derivative pairs. If you want to get in that deep, you can also implement your own layer. And when you're implementing your own layer in PyTorch, one of the things you have to define is what will my gradient calculation be like? And that's something you will have to define. And PyTorch basically defines all of that for us.
Mm-hmm.
Yeah.
That's also one reason why it's important to have operations that are differentiable. Because if they're not differentiable, you can't backpropagate over them. So that's why you have additions.
Yeah.
Mm-hmm. Yeah, pretty much. Yeah, that's as we said. Obviously, you need it to be differentiable. Things like ReLU, all that, they're differentiable for that reason. And so PyTorch will track through all torch.tensor objects as we pass them through models, loss functions, other operations, whatever you might. Okay. The word just didn't come. Anyway, so basically we tell PyTorch to only track the weights and that this is what we're taking the partials with respect to. And we do this for tracking to not happen we don't want to track too much because that'll just use up more computational resources, and we're already kind of starved for them. So we need to save as much as we can. And so with this, PyTorch can know the sequence of operations that'll take us from input X to output Y to loss L. And then we take partials with the chain rule, get our Jacobian, and just keep doing it until we get our model.
Okay, so a little bit more behind the scenes of like, how does PyTorch actually track all of this? And it does so using something called an execution graph. So basically, you may have the output here, your final loss, and it starts drawing, or like it keeps track of this graph as you're executing of like, oh, like to get to this loss, we need our Y labels and our activation outputs from the last function, which needs the output of the previous layer, and that output of the previous layer relies on the weights of that layer, the bias of that layer, and the activations from the previous layer, etc. It draws this almost like dependency tree of how you get from your inputs to your outputs. And basically what we can do is when we're actually calculating the gradients, we start from the loss here, and we do our multiplication backwards, almost traversing this tree. And the moment we get to a leaf node, aka a node that's like a weight and a bias, then we say, okay, when we get to a leaf node, that means we have calculated the gradients for the leaf nodes. Let's store that gradients within the tensor object of that leaf node, and let's just store it there. The optimizer will need it later. And it also does an additional check, which is we only tell PyTorch to track gradients for certain tensors, and these tensors typically here are also what's being tracked. So that's basically the idea of backpropagation. It basically, you start from the end, our loss, and we slowly propagate backwards, backpropagation, until we reach the very, very beginning, and we have calculated the gradients for every single one of the weights and biases here. Does that kind of make sense? Okay, yeah. And again, like here's a simple-ish example of backpropagation. We're looking at a fully connected layer. It's just here to show you that this is the math behind it. And with enough trying, you can backpropagate through any function. Here's an example of a relatively complex one, batch normalization. If this is our definition, this is how you calculate the gradients. It's a lot of math, but the key thing is we can reach the end at some point. This is a very long equation, but this is something that we can calculate, and this is deterministically defined. The gradient is always this, and as long as we keep track of these intermediate values, we can do backpropagation, right? So that's the idea of like why backpropagation is so important, because it makes it possible for us to calculate gradients relatively quickly. Because remember, GPUs, which is what we're training on our models on, are really good at matrix multiplication quickly, and a lot of them in parallel. Okay, so with that in mind, let's come back to the code, right? What we're doing here is when we're defining the optimizer, we're telling the optimizer which tensors are the leaf nodes, aka which tensors have tensor.grad, and we're tracking the gradients for. That's what we're passing it into the optimizer. So the optimizer knows what I'm optimizing. These are the tensors that I should update. Then optimizer.0grad, what it does is it looks through our list of tensors and it says, were there some gradient left over from the previous step? Let's zero it out. We want to start over again with the gradients. And then as we pass in our inputs and we make some predictions and we compare those predictions to our labels to calculate our loss, all of this is being tracked by PyTorch, right? So when we take our output loss and we do current loss backward, that's what's happening when I say backpropagate to all the leaf nodes and it's after tensor.grad. So what's happening here is it does, like our leaf backpropagation, right? We start from the loss and it calculates the gradients for every single one of these weights and biases. And it basically says, okay, now all the gradients of our leaf nodes, aka our actual model parameters for training, is stored in the .grad attribute of each of the tensors. Then optimizer.step just loops through every single tensor and says, okay, here's our tensor, here's our gradients, use that to apply to whatever we're, if it's just gradient descent, subtract that gradients with, multiply by our learning rates from the tensor value itself. If it's atom, then it does some more normalization stuff, but it uses the .grad property of that tensor to update the tensor itself. And then we have performed backpropagation. So one more important thing is whenever you do loss backward, what it does is instead of just storing the gradients to the .grad feature of the tensor, it actually adds to the .grad feature of the tensor. So the dograd like variable is basically a tensor of the same size as the original tensor itself, and it's initialized to all zeros, right? Because it does this addition work, and you can see how that may be useful if we say have multiple losses, right? Multiple ways of evaluating the model, and we want the gradients to add up to basically add up. Because of that, if we don't do optimizer.zero grad, what happens is we just keep adding to this dot grad attributes, and our gradients become very, very large and explodes. And that's not something we want. If we want to keep track of the gradients, we want our optimizer to do it, not just to crudely add to the tensor itself, which is why we have this optimizer.zero grad. This was a very important line that even I sometimes forget and go, why is my model not training? And why is it just going to NAM, which is not a number, aka infinity? It's because sometimes you may have forgotten optimizer.zero grad. Remember to clear your gradients every single iteration. Okay, so that's basically what I said. In summary, to train your model, you want to initialize it, initialize the optimizer, zero out the gradients, pass training data and calculate loss, use loss.backward to backpropagate through the derivative tree and calculate the derivatives of parameters, and use optimizer.step to loop through the parameters and perform the updates, whether that's cascading descent, atom with momentum, whatever you're doing. So here are some helpful resources. And that concludes the little presentation parts of what we have today. And now we're going to basically go through what that is, but in the actual project itself, right? You can see exactly the same thing happening. We have all the comments that match what we're talking about, right? Again, we have this part is being tracked by PyTorch. And then in this case, we're just doing optimizer.zero grad at the very end because we're basically saying, all right, now we have finished performing the updates, let's zero out the gradients. It doesn't really matter where you put this, just don't put it in between the loss and the optimizer.step because it clears out the gradients before the optimizer can make an update. So you can put it here, you can put it here, it doesn't really matter. But this is basically how the training loop works. And what this model.train does is for certain layers in your model, sometimes their behavior changes depending if you're doing training or if you're doing inference, such as batch normalization. So it basically just tells the model, hey, I'm actually training, please put yourself in training mode. And for testing, it's a very similar thing, but instead this time we make the predictions, we calculate how many correct outputs we have had, and we don't actually do this whole backpropagation loss that backward thing because that's not very important for us. So that's what the testing does. It basically puts a model evaluation mode, which basically says, hey, we're evaluating, we're testing, we're not training anymore, right? So that's very important. And one thing that you can actually do to basically make sure the model isn't calculating gradients during while you're doing testing, because when you're testing, you're just testing, you're not actually going to train a model, is you can actually use a function decorator like this, torch.no_grad. Basically what that does, or you can do something like with torch.no_grad, and then anything you put in here will not be like any operation you do in here will not be tracked by backpropagation. And basically what this does is it just tells PyTorch, hey, stop tracking the gradients. You don't have to do that. And it makes things a lot faster that way. So yeah, this calculates the accuracy and we can visualize the current model's performance. So when we run a train test loop, it becomes relatively easy. We have a bunch of epochs and we basically pass our necessary model and loaders in there. And at the end, we'll be able to see that that's a dog, I think. Yeah, so that's a dog. At first it thinks it's a frog, but we can see how the model slowly gets better, after it will slowly get better and better and better and better. And yeah, that is how you train a neural network model. So with some, last tidbits before I set you guys free and be able to try to train your own model with this code is you can see here torch.save. That basically what that does is it takes the state dict of the model, and what that is basically it is a dictionary that contains the name of the model's weights and the actual weights themselves. So it's just basically a bunch of PyTorch tensors, and those tensors represents the weights and biases of the model. And what this does is it just saves it as one big .pt file, which is basically you don't have to call it .pt or .pth. That's just a convention. It's just a file. Then PyTorch then can read. So we can actually load the weights by basically creating a new instance of the exact same CNN. That's very important, right? We want the exact same model because if we have weights and models that don't actually match in their dimensionalities, PyTorch is going to give an error. But you load the model with torch.load, which then you can load into the actual model itself, into load state dict, and you put the model to the device, to device, and this device, if you're wondering, is defined up here, all the way up here in the beginning. here basically says, if you don't have an access to a GPU, run on CPU, but if we do, we want to run on CUDA, aka that is the NVIDIA version of like their GPU API. So yeah, that is actually how you train a model. So and you can load the model as well, so you don't have to train it every single time. We can evaluate it to make sure like end of equal accuracy 71%. That's probably where our model is. And yeah, that is basically how you can train a PyTorch model from scratch. All of it. We have just three workshops later. You went from not knowing mostly what PyTorch is to being able to train your own model. So yeah, that's how you train a model. Any questions? Easy. No. But again, like you can see how there's many nuances of like how we can expand creating a model so much further, how we can change the way we train things. But what PyTorch is really amazing about is really flexible. You can, what happens is entirely dependent on you, right? And you can define how a model is being trained, with a training loop. You can define how a model goes from input to output with the model definitions. You can change how the optimizer is actually optimizing your network with like the different pre-built optimizers, or you can build your own optimizer for that matter. I've done that before. It's kind of fun. Yeah. So okay, what we're going to do right now is a little basically next week we're going to be talking about embeddings, RNNs, LSTMs, and transformers. The latter of which is the backbone for ChatGPT and many other large language models. We're going to be talking about how to analyze time series data. That is the attendance code design backprop by hand. You will be doing that in ECE 747, which in my opinion is still one of the best machine learning courses there is. It is being offered next quarter. If you're a second year or above, I highly recommend taking it. If you're a first year with linear algebra experience or a brave soul, you can take it as well. But yeah, so the rest of the time, I'm going to basically make it a little like work session where you can play around with the notebook, ask us questions, and see what sort of training accuracy you get by the end. Feel free to modify the model. But yeah, if there's nothing else, hope to see you next week, and I hope to see what model you create for the next, I don't know, like 30 to 40 minutes.